All right, so thank you all for joining our panel on energy transmission. With me today, I have three amazing panelists. So I have Dr. Johnny Huang, or Huang. Yes, Huang is the co-founder and president of Teratonics, which focuses on commercializing RF harvesting and RF-based wireless power transmission technologies. With a PhD in applied physics and an MBA from Columbia University, he has a deep background in strategic planning, financing, and managing technology startups, so he can do it all. He's passionate about clean energy and energy harvesting. Dr. Sudeep Mazumdar, who you can't see because his video is not working, unfortunately, is an expert in power electronics. He is a professor and the director of the Laboratory for Energy and Switching Electronics Systems at the University of Illinois in Chicago. He's also the president of NextWatt, LLC. Mazumdar has around 30 years of professional experience, has held R&D and design positions in leading industries, and served as a technical consultant for several industries. His research has yielded over 50 sponsored research projects and has received many awards, including Inventor of the Year and the UIC's Distinguished Researcher of the Year Award in 2020. Johnny Kessler is the Senior Account Executive at GovPlace, where he helps companies take a strategic approach to technology-led transformation and modernization to improve business and operational efficiency. So thank you all for joining me, panel. We've got a really high quality panel here, lots of knowledge going on. So the first thing I want to know is I want to give you each around 90 seconds to tell us where you believed energy transmission is currently in our world today. So I'm going to start with you, Sudeep.
Yeah, thank you. Can you hear me?
Yes.
Okay, yeah, so thanks a lot basically for the opportunity. So I'm kind of delighted to be on this panel with so many of these other experts. So I think with energy right now, the clear shift, I mean, my background is in power electronics. One of the clear shift that we see in the power electronics space is a need for meeting multiple metrics simultaneously. So we are not only talking about meeting efficiency, but basically efficiency, high power density, specific power, economy of scale and cost. So this is a major challenge we see. In terms of like the landscape of the energy, it's changing from traditional carbon or fossil fuel based energy sources to more like renewable energy sources. And so that is going to have an impact, not only going to have an impact, it's already having an impact in terms of distribution and at the transmission level as well. So basically moving away from traditional energy sources to sources like solar and wind and whatnot. And associated with that one are issues with energy storage, so battery-based energy storage and things like that. And it's also having an impact on the mobile sector. So just not the stationary energy systems, but also mobile sector like electrical vehicles and others. So we're going to be talking a little bit about it. So a lot of things are basically going on in that regard.
Awesome. And Johnny?
Yeah, thank you for, and by the way, saying that a lot of smart people. I'm the lowest of the rung here, but I'm the geek that connects it all together. So I like to what I believe, or what I'm hoping to get out of the AFWERX challenge and the interactions that we have here is hoping that we can help the government find quick and easy ways to get renewable energy technologies and transmission in their hands. I mean, again, finding easy ways to get them. And I know we're going to talk about our passion, but that's one of mine, is finding something that the government can do now and also in the near future and then the far future about enabling renewable energy and using those technologies to, again, get us to that zero carbon footprint.
Johnny?
Hi, Heather. Thank you. So you can call me Johnny H, I guess.
Johnny K and Johnny H.
Yeah, so I think we definitely have made a huge progress since I think Nikola Tesla tried to demonstrate wireless power transmission about a century ago, right? So there's a lot of technology to try to deliver power, as Sudip mentioned, over different distance, different power level, and different equipment size, right? So people have been using, ultrasound, laser beam, and electromagnetic wave, particular RF wave, which we know a little bit more about it, given our background in energy harvesting in RF space. So I'll see there's a lot of progress in various technology. Particularly, I think I see a huge opportunity in radio frequency or RF-based wireless power transmission. Given the background, we're going to immerse in a very strong 5G network. Basically, we're going to be surrounded with a lot of RF signal around us, right? All the related technology are maturing. So that's where I see there's a lot of opportunity.
Very cool. So can you give an overview of wireless power transmission technology? I'm going to ask you, Johnny H.
Okay. Yeah, I'll expand a little bit on what I just described. When we say wireless power transmission, people also call it wireless power beaming. Essentially, we try to deliver power to a remote inaccessible device or equipment. So we're all familiar with, for example, Qi-based Qi type of charging device, right? It's over a very short distance using so-called inductive coupling over a few millimeter space. And I have seen company using ultrasound to deliver several watts over 10, 20 feet distance. I think Naval Laboratory last year demonstrated using laser beam and photovoltaic technology to deliver several hundred watts over probably 500 meter space. These are larger systems. And there's quite a lot of team and company has demonstrated RF-based wireless power transfer can be at the lower end, can be, for example, using either Wi-Fi or cellular source or local RF beam to deliver microwatt or milliwatt level power over 10 meters over 100 meters, based anywhere you have a strong RF signal, or use a dedicated large system deliver several hundred watt to even kilowatt level to a drone or UAV like a few meter away, right? These are the interesting area that people already have some initial solution. I think the main challenge is really how to deliver them in a very high efficient way at lower cost at the desired even portable size, allow you to have a mobile delivery system. Right? These are the interesting area we and many other companies are trying to working on.
So, Dr. Mazumdar, why do we need fast battery chargers?
Hi, sorry, I was on mute. Yeah, so I think one of the challenge with electrical vehicles, whether it is for commercial applications or basically for non-commercial application, is the range. Because if you're going to be replacing fossil fuel-based vehicles with electrical vehicles, then that is going to be a key aspect. So currently, the energy density of the batteries, I mean, a lot of research is going on, a lot of progress has been made. But if you compare to, for example, the density, for example, in digital electronics like RAMs and others, the energy density of the battery is not really going up at that rate. I mean, it's nowhere near, which simply means that if you want to extend the range of an electrical vehicle, you're just going to be needing a bigger battery. And so there lies the problem. The thing is, if you're going to have a bigger battery for a bigger range, longer range, then it's going to take you just that much more time to charge it. So you need a very fast charger so that you can charge the battery quickly, a larger battery, and you can use that larger battery to basically travel kind of longer.
So what are the challenges that you see in creating these technologies?
I think the challenges are like multiple fold. I alluded to some of them earlier. So right now there are these two classes of chargers. One is basically the chargers that are outside the vehicle, that are called off-board chargers. And then there are basically chargers that are on board. So the way to look at it is that if you're going to be placing a charger on board within the vehicle, then you have to take something out of the vehicle, so to speak. And so the space becomes a significant constraint because you're taking some things out, you're going to have limited footprint in which you can put it in. So power density is a major issue. It's sort of a technical term. It simply means power density is like, how how much power you can put in a particular volume. So that number goes very high. So in other words, you have to put in more and more amount of power in a smaller amount of volume. The second thing is that simply because something is small, that doesn't necessarily mean it is going to be light. You still have to make it light, and that is basically specific power. You have to make things which is very compact. You have to make things which are basically going to be very light. And then the thing is, you have to make it very efficient. For example, if you have something which is very compact and everything, thermal becomes an issue. So if you have higher losses, then the thermal overload is going to be a problem. So you have to make it efficient. And then, of course, the challenge is cost. You have to make things kind of cheap enough. It may not be the sole driver for DoD, but I would say the thing it is still just as much of a driver for DoD as well. So there are multiple of these challenges in here, but I alluded to a few of them. Yeah. And then there is one more, I just slipped my mind, which is regulatory issues also, because there are so many different technologies going on.
So, Dr. Huang, many say that wideband gap technology is a key enabler. How so?
To me?
Mm-hmm.
I thought this is probably for Sudip, right?
Oh, well, if you want to toss it to him, then go ahead.
Yeah, I can take a crack at it.
That'd be great, yeah.
I think so when we say wide bandgap technology, what does it exactly mean? I mean, the normal device technology is silicon based, right? I mean, this is a significant amount of kind of penetration in the market today. One of the reasons is it is it is so low cost. So when you're talking about wide bandgap technology, you're talking about different type of materials. Like the most commonly used materials today are like silicon carbide or gallium nitride materials. One of the properties of these materials are the thing is they enable you, in simple terms, they enable you to operate at a higher voltage. They can actually tolerate, let's just say, high electric fields, in some cases, high thermal stresses, for example, significantly more than silicon devices. So therefore, if you have a material which basically has this property, when you make a device out of it, so this device can take a significantly more beating in terms of higher voltage and higher thermal robustness, let's just say. So now you can potentially make electronics, like for example, charger or wireless power, let's just say, they can operate at significantly high frequencies. Because normally if you try to operate at such high frequencies, you will have some challenges, with the devices. So now with these type of materials and devices based on such technologies, they are basically game-changing technology. So they enable you to operate at a higher voltage. So when you operate, for example, a higher voltage for the same power, current goes down. It has impact on efficiency and reliability and all of those. Cost is an issue, but the cost is coming down pretty significantly as the market acceptance is there. Yeah.
Very cool. I'll throw this one to the group. While a battery charger charges the battery from the grid, can power extracted from the battery be fed back?
Sorry, I mean, maybe I can take a crack at it, maybe others can. So I think this is something we were developing, some of these type of technology. So there was a request from the Department of Defense, some personnel that when we were actually giving an exposition. And so they have basically vehicles. So essentially what you have is that if you have an electrical vehicle, you have a large battery inside. And so what a charger is doing, it is charging it so the vehicle run on the battery for a long period. But what if the vehicle is not running all the time? You still have the battery with this enormous amount of charge. What do you do with it? So one of the things you can do it is, instead of taking the energy from an AC grid and charging the battery, can you actually take the energy from the battery and feed it into a grid? So for example, Department of Defense has some of the forward operating bases, and they may not have access to a reliable grid. So now you have that untapped energy source inside your vehicle. And if you have a few of these, and if you can harness that energy back into the grid, this vehicle actually can have the dual support. So the answer is, yeah, I mean, this type of technology will have pretty significant impact if you have this bidirectionality of power flow.
Yeah, I just want to add one comment. I think there's quite a few startups already having this kind of business model using, say, Tesla battery to as a storage, as a distributed storage, household storage unit, right?
Yeah, the Tesla Powerwalls are they're pretty economical for what they do, and they're bringing it to the masses. And I just wanted to put in a reminder that if any one of our attendees have any questions that they want to ask the panelists, feel free to type them into the chat. So what are the if you're trying to create a wireless transmission, like an energy transmission device, like that's wireless or any other kind of this, like what are the key components that you would need to do this? Dr. Huang?
Yeah, thank you. I mean, generally speaking, you definitely have a good power source, right? At a low cost, the desired power level, and yeah, power level. And then there's the receiving end. Whether if you use the RF wave or millimeter wave based transmit system, then people typically use a rectangle based receiver to receive the energy. And there's also associated antenna, advanced antenna design and power electronic circuit associated with that. Yeah.
So I was going to show on my desk here, I actually have one of those light bulbs that is hovering above the energy source, but I realized there was no way for me to easily show it. But they do actually sell, just like as a desk toy, like a bulb that is powered, like I guess like the Tesla example of, I mean the Nikola Tesla example of like the light bulb being powered. So I mean there are fun examples of this, not just the mass scale. So what are some of the challenges and opportunities in wireless power transmission? Johnny K.
Well, some of the challenges obviously have to do with hardening of these devices because they can be sensitive to other basically attack. That's another reason we have to kind of take that in mind when we're talking about AFWERX. Is sure, we're talking about science fiction things, but when put in a practical application, you have to take into account the hardening of the devices, making sure that they're secured and they're not prone to attack, and or in that also is attack from physical attack and or cyber attack. So cybersecurity is also important to make sure. So that again, that's some of the challenges they're dealing with. Obviously, some of the technology is fairly new. Johnny and Sudeep are much more versed in that when it comes to the technology that's actually used for the transmission. But you know, and they can talk. Johnny or Sudeep, do you have anything more to add to that?
Yeah, I would just say a few things specifically to the RF-based wireless transmission system. There are a lot of effort in the RF power source. People have already done using gyrotron or using maser, basically microwave laser, or gallium nitride based RF power source. But you know, we still hope there will be really commercial level, low cost power source. On the receiving end, I think that it's desirable to use to develop a so-called a system using high RF frequency, up to even several hundred gigahertz. The benefit of that, allow you to have a smaller beam size, can deliver to a further distance with higher efficiency. So in order to do that, you need to have really a high efficiency rectangular receiver, and that's posed a lot of challenging on the key component. For example, the semiconductor diode. You need to have a diode to work up to several hundred gigahertz or even terahertz cutoff frequency. There's quite a lot of effort. We're also working on that. We have a potential solution there. And there's associated high-speed electronics. That's also a challenge. I think people have done a lot of great work.
Yeah, I think just to add to what Johnny was saying, which is that I think right now there's been a lot of change going from silicon to wide bandgap, especially with the gallium nitride. The kind of devices you can actually develop using this type of materials, at least in some specific instances, they provide features which are just not available in commercially available silicon devices. I think the new materials that are coming in ultra wide bandgap, that'll also be quite useful, especially taking the power capability of these devices, because now you'll be able to operate at higher voltages, and you can also go to like EHF band type of things if you want to go there. I guess with regard to the cybersecurity issues, yeah, so we are doing currently a project, and so it is a real challenge, especially when you are, because especially at the applications where energy and the data are reaching parity in terms of energy level, let's just say, right? I mean, you're powering IoTs, which is not requiring a humongous amount of energy. It just, there are so many of them. So that is an issue, but it's sort of like with many technologies, there are flip side to both the things. You just have to figure out like workable solutions. But yeah, there are some concerns. I'm doing projects in solar inverters, for example. So there are concerns that people can, if you're creating the network through wireless, if somebody could actually hack into that one and basically start manipulating your references, for example, that'll be a disaster if inverters are connected to the grid and somebody just tapping into the system and then basically changing your setup. So we are trying to kind of pose solutions on it, but this is an ongoing research challenge.
Yeah, I mean, part of the hazard question is also about opportunities. The 5G is at the early stage of deployment. We're going to see a lot of cells, high-speed signal around us, RF signals, right? So these are primarily used for deliver data. But why don't we turn that into a power delivery system? Things are already generally available, particularly for low power device like IoT sensors, like the wearable on the on soldiers' uniform, like implant medical device. Potentially, all these can be used powered by the RF-based wireless transmission system.
Are there any dangers to having this wireless energy in the air? I know there's a lot of people out there that believe that there's a lot of danger to this. So what would you say to them?
I mean, definitely we need to follow what the guideline provided by FDA and FCC, right? So, but the current technology, even within the well below the required level, is already can power the lowest sensors. I mean, the technology are made so rapid development such that they're requiring microwatt level or milliwatt level power. These are, I would say, so far no scientific data show they have evidence. Maybe in a few generations we'll see the result, but at least until this point, we look like we're in a slow microwatt, but we're doing well.
Great. So what is being done to eliminate single points of failure in these various deployment scenarios for energy transmission?
Who did you say?
So like to make sure that nothing goes wrong.
So again, much like my background in IT management, you just want to make sure that you have reasonable efforts for eliminating single points of failure by hardening devices and or having multiple routes. So again, making sure that we can redirect the energy if it's been interrupted for one reason or another, or and that's, again, the interruption can be external or internal if we have a failure inside. And then also hardening of devices is important against, hardening from making them more stable and or keeping them from being vulnerable to outside forces or influence to make them not function anymore. And again, if anybody else has anything to add.
I also just add on a little bit on what Heather asked about the power level, right? So definitely if you want to transfer watts or several hundred watt level power, we don't want to do that in the downtown area, right? But these are applicable in space, right? When you power a flying drone in the space, I think the safety level probably can be more relaxed for high power transmission. Or maybe on the moon base where there's nobody around, you can really beam as high power as you want. Yeah, I think definitely for high power transmission, we need to consider the specific user case.
And I mean, for everything you do, like with that on the moon, for example, that could be a way to generate heat as well. So whenever, I mean, that's something that they are on our previous panel, they were talking about low energy scavenging, and your byproduct is heat whenever you're generating that kind of energy. So for something like the moon, that could be something that they are thinking about.
Yeah.
So what cybersecurity protection should we look into with modern transmission technologies? I know you touched on this earlier, Sudeep, but this is open to the group. All of you, there's been a lot of breaches. I think there was one earlier today in Florida with a water plant. So when we have this point of failure, I mean, this is a utility. what can we do to make sure it's protected?
I think probably Johnny is has a broader experience and deeper experience on this subject. So my experience I can share with you based on some work that we are doing right now, and some work I actually did a few years back, sort of related to this one. At that time, the cybersecurity was, people recognized it, but now it is becoming an issue. I think what I'm realizing it, which is that there is basically this. So when you're talking about this type of sort of mitigation, so one important issue is the detection aspect of it, what is called an intrusion detection. Then the second aspect of it is which is called intrusion classification, and then basically the intrusion mitigations, which is the one that we talk about a solution. And these broadly fall under sort of what are called proactive and reactive approaches. So let me explain a little bit. A proactive approach would be where you're looking for solutions so that if you have a real-time system, because sometimes you have real-time systems, they are so fast that you'll not have time to, you'll not have a time to do a lot of thinking. It is so, for example, Johnny is talking about some of his wireless power. These are probably in several megahertz. 1 megahertz is a microsecond. You don't have time to react, I mean, and that speed. So a proactive mechanism is very important, like methods like blockchain and other type of things. However, you also need reactive mechanism. The reason is that proactive mechanism typically are based on what you know, okay, and what you can anticipate. But just like you know what are the vulnerabilities, probably your adversary also knows very well what your vulnerabilities are. I mean, they probably are looking into the same thing. So they'll be looking at trying to attack your system in a way that you may not have, seen in the past. So what do you do in the meantime? If you got a system which is designed to kind of blunt attacks that are known, but if you get attacked with a different event, let's just say, you still have to kind of maintain your system. That's why the reactive aspect comes in. So one of the projects that I'm doing, it is this aspect has become really, really tough. So this is the way I see it is you need some sort of a combination of proactive and reactive mechanism, and you need some sort of a multi-scales. So I work in the area of power electronics. So if you go deep down to the device level, the energy is harvested at a mind-bogglingly high speed, right? But if you go to grid level or things like that, so if you're talking about policy, okay, or if you're talking about economics aspect of the grid, this is happening at a much slower scale. So an intrusion could have effect on multiple levels. And so you need to come up with multi-scale strategy. You need to have a proactive and reactive mechanisms, okay? And it needs to be adaptive. It's a constant game changer. It's kind of difficult to basically do it. But the thing is, somewhere the solution has to be in addressing some of that. But Johnny can probably explain better.
Go ahead.
Go ahead, Johnny.
Johnny K, sorry.
Oh, Johnny. So also wanted to bring up as far, just making sure that your agency and organization is meeting typical standards for cybersecurity, but also you want to make sure you always maintain the human element of cybersecurity. Make sure people understand how these infiltrations happen. How do they originate? Go through the process of teaching people how to watch. Number one, that's more often than not, cybersecurity events are because of a human error, and because somebody wasn't watching and or somebody wasn't thinking. And so making sure that your staff, number one, that you have them meet the minimum requirements and even go for the maximum requirements of things like FIPS 140-2 and DHS 4300, but also make sure that they go through the training programs to understand, how do I make sure that this computer is secured from outside influences, and or how do I keep that from happening? Again, the policies of don't plug devices in, don't. So again, just always, that's probably one thing that most people forget is you can have everything protected from the outside, but it's from the inside that causes your weakness.
Okay, and thank you very much all. I'm told that they're finished on the main panel, so I want to thank everyone, and attendees, please return to the live screen. So thank you, doctors, and Johnny Kessler from GovPlace. Bye.
Thank you.
Thank you very much. Bye-bye.